Hello and welcome to the next video of our channel Practical Hope. In this video we are going to do computational analysis of the behavior of a collection of particles in a box that satisfy Newtonian mechanics and interact via Lennard Jones potential. This video is in continuation to our previous video on molecular dynamics. So this is part 2 of that. In the previous video we have already studied classical molecular dynamics simulations, that is NVE system. These are the 4 curves that we have already discussed in our previous video. Let's focus on the energy curve. Here you can see that kinetic energy is initially increasing, and once equilibrium is reached, it fluctuates about some average value, whereas total energy is fixed, since we studied NVE system. Next we are going to discuss NVT system, where temperature will be kept constant instead of total energy. So here comes the concept of thermostat. Let KEI is the initial kinetic energy per particle and KE is the kinetic energy per particle at time t. So we define scaling factor for kinetic energy SK, KEI divided by KE, and scaling factor for velocity is square root of SK. So we have to rescale all the velocities by multiplying with scaling factor SF. In this way, the kinetic energy and hence temperature can be kept constant. Now this rescaling can be done in 2 ways. First, we can rescale velocities after every iteration. Kinetic energy and hence temperature will be absolutely fixed. It is comparatively more time consuming because we are rescaling in every iteration. So here you can see kinetic energy is fixed. We can also rescale after fixed number of iterations, say 100. Kinetic energy will fluctuate but only about some average value after equilibrium. Average temperature will be fixed. So here you can see this step is because of the rescaling, then again second rescaling, then third, and so on. So after every 100 iterations we are rescaling kinetic energy so that its average value remains the same. There might be some fluctuations but the average value will be same. Average temperature will also be fixed. This second technique is little bit faster because we are going to rescale after 100 iterations, not during every iteration. Also we can study fluctuations, which we cannot do in the first way. This is the code for implementing the concept of thermostat. Vx, Vy, Vz are the rescaled velocities. Name of the function is thermostat. Vx, Vy, Vz are the input velocities. K is the kinetic energy. So first we have to define scaling factor SF, that is square root of KEI by KE as discussed earlier. Then we define a for loop that will run from 1 to NP, NP being the number of particles. Then we will rescale Vx, Vy and Vz by multiplying them by scaling factor SF. Finally, end function. Now before implementing it in the main program, let's discuss another concept, how to speed up the simulation process, the concept of neighbor list. Which part of the simulation is consuming most of the time? Distance calculations. To calculate force on a particle, we have to calculate its distance from all other particles, but only those particles will exert force which are at a distance less than cutoff distance RC. Rest of the distance calculations become irrelevant. We can save some time by minimizing these irrelevant distance calculations. To calculate force on the particles, instead of calculating the distance from all other remaining particles, we are going to define a neighbor list, that is list of particles within distance Rs for every particle. Because of limited velocity, particles beyond Rs will be able to interact with the considered particle only after some time or iteration, say 100. So for 100 iterations, particles will be able to interact only with the particles defined in their neighbor list. Say this is the box having a fixed number of particles. Let's consider this particle. To calculate force on this particle due to all other particles, we first need to calculate its distance from all other particles. Once we do that, we have to check how many particles are within this cutoff distance RC. As you can see in the figure, there are only 3. So only 3 particles will be able to interact with the center particle. Here we are going to define a neighbor list, and instead of calculating the distance of the central particle from all other particles, we just need to calculate its distance from the particles within the blue circles. Particles within the blue circle are the neighbor list of the center particle. Out of all the particles in the blue circle, we are going to check which particles are at a distance less than cutoff distance RC. Then we can calculate the force on the central particle. For fixed number of iterations, say 100, the neighbor list will remain the same. After 100 iteration, we'll have to change the neighbor list again because particles keep on moving and the neighbor list will change with time. While fixing neighbor list for 100 iterations, we have to make sure that these particles outside the blue circle may enter blue circle, but they should not enter the green circle, so that they will never be able to interact with the central particle for the next 100 iterations. Similarly, we have to define the neighbor list for all the particles in the simulation box. Few things we have to consider. If RS is too large, there will be a large number of particles in the neighbor list and simulation will be slow. If RS is too small, there will be small number of particles in the neighbor list and simulation will be fast, but there is also possibility of error. Furthermore, in some systems, there might be the formation of some clusters that also we need to take care of. Say this distance is delta R, so RS is equal to delta R plus RC. RC we already discussed in our previous video. It's the cutoff distance and has been set to 2.5. So we just need to calculate this value of delta R. How to calculate this distance delta R? For this, we are going to use this Maxwell speed distribution curve. Here you can see all the particles have velocities less than 5. So we take Vmax equal to 5. dt has already been kept as 0.005. So maximum distance traveled in 100 iterations delta R 100 equal to 2V dt Ni. This factor of 2 is because the central particle is also moving. So if two particles with velocities v move towards each other, then the relative velocity will be 2v. That's why there is this factor of 2. Let's put the value of v, dt and ni. So delta r is 5. Rs should be greater than rc plus delta r. So rs we are taking as 8. Next, how to define the neighbor list. Say we have n particles in the simulation box. First, we are going to define the number of neighbors each particle has. Let's say first particle has 8 neighbors, second has 7, third has 20, n-1 has 18, nth particle has 10 neighbors. Next, we have to define the index of these neighbors. These are the index of the 8 particles or neighbors of first particle. 3, 5, 8, 10, 12, 18, 22 and 30. Similarly, we can calculate for second particle and so on. While defining this index of neighbors, we have to take care of one more thing. As we already discussed in our previous video, Fij is equal to minus Fji because of Newton's third law. That is, force on particle 1 due to particle 2 is equal to minus of force on particle 2 due to 1. Suppose particle 3 is the neighbor of particle 1. So, in the first case itself, we will calculate force F13. Then we can also evaluate F31. So, while defining the neighbors for particle 3, we don't need to include particle 1. Because we have already calculated F13, so we don't need to calculate F31. This is the code to implement the neighbor list. We have defined a function. NEIGHNA is the vector having a number of neighbors and nlist is the index of neighbors. Name of the function is neighbor. XYZ are the position vectors. Name we are defining initially as 0. We'll update it. This function is somewhat similar to the force calculation function, the function that we have defined for calculating the force in our previous video. So you can see first we have defined a for loop that will run from 1 to np minus 1. x1, y1 and z1 are the coordinates of ith particle. Then we have set another for loop j that will run from I plus 1 to np, and x2, y2, z2 are the coordinates of jth particle. Then we have calculated dx, dy and dz. And then we have checked this condition. If absolute value of dx is greater than lx by 2, then dx is equal to lx minus absolute value of dx multiplied by minus dx divided by absolute value of dx. These three if condition we have already discussed in the previous part of this video, so we are not discussing them again. Then we calculate this value of r, that is square root of dx square plus dy square plus dz square. Once we know the distance, we will check whether this distance is less than or greater than rs. If r is less than rs, then we have to increase the number of neighbors. Ne I equal to ne I plus 1. So we have increased one neighbor. And we also have to save the index of neighbors. So nlist bracket I comma ne I equal to j. J is the index of the neighbor. In this way, we will be able to save the number of neighbors of all the particles as well as the index of the neighbors. Finally, end function. Let's implement in the program now. This was the program that we wrote earlier. Change the title. Instead of NVE, we are going to study NVT system. We are also going to implement the concept of nearest neighbor to make the simulation fast. Let's change number of particles to say 1000. We are keeping other constants as same. Since we have considered 1000 particles now, along the 3 axes we have to define 10 points. So P1 should be 1, P2 should be 19 and DP should be 2. So there will be 10 points along each axis, 10, 10, 10, total 1000 points or 1000 particles. One more thing, this x1, y1, z1 we have also used in the function where we have initialized the force. You can see x1, y1 and z1. It's not affecting anything, but still it's better not to use x1 again. So let's change it xi, yi and zi. These are the initial positions. Change xi, yi and zi in the scattered 3D plot. We don't need this replot function anymore, so delete it. Now we have to first implement the thermostat function. We have already written it, so copy and paste here before the main program. We also have to define the KEI, that is initial kinetic energy. We can calculate this value of KEI while initializing the velocity components. So write KEN, kinetic energy. Now we need to calculate this kinetic energy in this well init function. We don't need to write it because it's already written where we are updating the velocity. So we can copy from there. So copy and paste. Here we get the value of initial kinetic energy while initializing the velocity components. We also need to write KEN here where we are calling the velocity initialization function well init. KEI equal to KEN divided by NP. So we get the initial kinetic energy per particle. Next we are going to call this thermostat function in the main program after every 100 iterations. So check equal to modulo k comma 100. When k will be 100, 200, 300, then only check will give 0. So if check equal to 0, then we'll call the thermostat function. We don't need to write. Let's copy this thermostat function and we can paste here. Here instead of k kinetic energy, we have to write ke bracket k because for every iteration kinetic energy will be different. Then end. Copy this neighbor list function, paste it before the main program. So this is the function neighbor to calculate the neighbor list. We also need to change the function to calculate the force, since now we are not going to calculate the force by checking all the particles. We just need to check the neighbor list. So some modifications need to be done. First, the inputs, because apart from XYZ we need the NEIGH and NList, that is list of neighbors and the index of neighbors. Then delete this x1, y1, z1 and instead of I plus 1, now j will start from 1 to ne I. Ne I will give the number of neighbors for the ith particle. Delete this x2, y2 and z2. Define pp equal to nlist I, j. So this pp now will give the index of the neighbors. Instead of x1, xi, instead of x2, it's xpp. Similarly, instead of y1, it should be yi, instead of y2, it should be ypp, and instead of z1, it should be zi, and instead of z2, it should be zpp. Now we'll calculate dx, dy and dz for the nearest neighbors only. This J should be replaced by PP, since now PP particle will be the neighbor of ith particle. Since we are going to change the neighbor list also after every 100 iteration, so let's call this neighbor function here na, nlist equal to neighbor x, y, z. Now after every 100 iterations, neighbor list will get updated. Copy this and paste here. Since before calculating force for the first time, we are also going to need this neighbor list. Give two more inputs na, nlist to this force calc function. We forgot to define this value of rs equal to 8. So these are the constants. Then we have initialized positions. Then initialize the velocity. Actually this is not initialize the force, this is to calculate force. So this is the function to calculate force. This is the function to update positions. This is the function to update velocities. This is the function for thermostat. This is the function to calculate the neighbor list. This is the main program where we have initialized position, then save the initial positions, then velocity initialization, then calculate neighbor list and force calculation, and finally we have our program that will run from 1 to number of iterations 2000. These are the plot functions that we already discussed in our previous video. Let's run the program. Now this program will take time, so we are skipping and let's jump to the final result. These are the 4 plots. First plot is showing the initial positions of the particles, second showing the final position of the particles, third showing the kinetic energy, potential energy and total energy, and fourth plot is showing Maxwell speed distribution curve. This simulation took about 1 hour. However, if we don't use this concept of neighbor list, then this simulation will take about 4 hours to run. So we are able to save a lot of time using this concept of neighbor list. Finally, the units. We have not discussed units yet. Let us consider the case of argon. For argon, sigma or L is 3.4 angstrom. Mass is 40 mu, so it is 68 into 10 raised to the power minus 27 kg. At 300 Kelvin, energy is given by this. We can calculate time equal to square root of ml square by E. So what we are considering here is L or sigma is the unit of length. So if we are considering one length, then that means 3.4 angstrom. 68 into 10 raised to the power minus 27 kg is the unit of mass. E equal to kT is the unit of energy. And small t is the unit of time. So actual time interval will be 0.005 multiplied by small t. For argon, epsilon equals to 1.654 into 10 raised to the power minus 21 joules. We can also write it as 0.4 kT at t equal to 300 Kelvin. We are writing in this form because kT we are considering as the unit of energy. So we are writing epsilon in terms of kT, 0.4 kT. In the main program, we are going to change the value of epsilon from 1 to 0.4 for argon. Let's change the value of epsilon from 1 to 0.4 in the program. For better accuracy, let's change the number of iterations from 2000 to say 3000. We also need to multiply the expressions for force and potential by this epsilon EP. So FC should be multiplied by EP, VC should be multiplied by EP, F should be multiplied by EP, and finally V should also be multiplied by EP. Now in the hist plot, write this normalization equal to percentage F. So now at the output we are not going to get the normalized Maxwell speed distribution curve. We'll get dN by dE. So write Y label dN by dE. This E is not kT. dN by dE represents the number of particles in the particular energy range dE. Let's calculate the values of average speed and root mean square speed. V average equal to sum bracket velocity divided by NP, that is number of particles. VRMS equal to square root of sum of velocity dot star velocity divided by NP. Let's display the average speed and root mean square speed. Run the program again. This program will take time, so let's jump to the final result. After 3000 iterations, the average speed is 1.598, root mean square speed is 1.73. These are the 4 plots displaying the initial positions, final positions, energy of the particles and Maxwell speed distribution curve. That is variation of dN by d with speed of the particles. We can see from the 4th plot that the peak we are getting at speed of 1.5. Most probable speed is 1.5. So we have got all the 3 speeds: most probable speed, average speed and root mean square speed. From simulation results, VMP is 1.5, V average is 1.598 and VRMS is 1.73. As we discussed earlier, VMP is 1.5 sigma by t, because sigma is the unit of length and small t is the unit of time. We have already calculated the values of small t, and sigma we have already discussed is 3.4 for argon. So if we put those values, we get VMP as 370 meter per second, V average as 394 meter per second and VRMS as 426 meter per second. We can also calculate the 3 speeds theoretically using these expressions at 300 Kelvin. At 300 Kelvin, these are the theoretical values. You can see average speed and root mean square speed are quite close to the theoretical ones, whereas most probable speed deviates from its theoretical value. It's because a lot of particles are colliding and sometimes the peak shifts. We can also study the effect of temperature or particle mass on VMP, V average and VRMS using molecular dynamics simulations. Then we can also study the transient behavior and approach to equilibrium for an isolated system. These are the curves. First plot is for 125 particles. Here you can see initially kinetic energy is rising up and then slowly it is decreasing and reaching the equilibrium. This decrease of kinetic energy is varying with the number of particles, and as we increase the number of particles from 125 to say 1000, then this dip almost vanished, and for 1000 particles the kinetic energy initially increases and then again it slightly increases and reaches the equilibrium value. We can also study the relationship of large N and the arrow of time. Now what is this arrow of time? Suppose we have this simulation box. Now if we simulate this system, some of the particles will move towards the right. Now if we again simulate this system, reverse in time, then particles get the original positions if the small number of particles are considered with small simulation time. Particles can't get their original positions by simulating in reverse direction if large number of particles are considered and the simulation time is also large. Let's consider an isolated system of 512 particles. Say this is the initial state of the system where we have kept all the particles on the left side, and now if we simulate say 1000 times forward in time, then we get the final positions of the particles like this. If we simulate the system backward in time for 1000 iterations, we get something like this. There might be some numerical errors because of round off, otherwise we will be able to get more or less the initial state. But if we simulate say 5000 iterations forward in time, we get something like this. And if we simulate 5000 iterations backward in time, you can see now we are not able to reach the initial state. So by taking large number of particles and simulating for a large number of iterations, we will not be able to retrieve the original state of the system. This is the relationship of large N and the arrow time. Finally, we can also study the number density of the particles. Say we have considered all the particles on the left and with simulation they move towards the right. Let NP be the number of particles on the left. We can study the variation of NP with time. We can see with increase in time or number of iterations, the number of particles are decreasing and thus reaching the equilibrium value. Similarly, we can do for 216, 343, 512 particles. you can see the difference in the transition behavior as well as the equilibrium state. Now, of course, this NP is not the number density. Actually, it is the number of particles, but you can anyway divide it by the volume and get the number density. So, this local number density, how it is varying during the transition state and what is its variation in the equilibrium state for different number of particles that you can study. These are some applications of molecular dynamics simulations. There can be many more things that you can do with molecular dynamics. I hope you like this video. Share it with your friends and colleagues, and don't forget to subscribe our channel if you haven't done it yet.